So this workshop covers 3 different classes. So it starts with EE228, that's your continuous signals. Then 328 is discrete time signals. And then 419 kind of mashes up the concepts from both of those and focuses more on the applications. And so we're going to try and get to 419 material as much as possible, just because it's a lot. What am I trying to say? That's actually where you're doing stuff. 228, 328.
Most applicable.
Yeah, 228 is very math heavy, especially. And both of them are very math heavy, and you do need the math to get a deeper understanding eventually. But you can do a lot, not without math. You still need math, but with a more conceptual kind of understanding. So anyway, the systems that we're going to focus on, we're looking at discrete time systems because we're working in the computer. And so basically system is just, it has signals that come in and signals that go out, and you're kind of looking at how it changes those signals from input to output. So you have common examples would be, you have a modular synth, like what we're making right now in AES. So we made the VCO, right? And then that's going to output the signal. We're going to feed it into a filter or something. And then you have that also with guitar pedal boards. And then if you have any audio workstation software in your computer, Ableton, for example, that's just another system essentially.
Yeah.
Yeah, signals are discrete. We're looking at them signals in both time and frequency. And yeah, like I said, we're going to try to avoid the heavy math and look at the applications. So if you have MATLAB, you should be good to go. Cool. There are a couple functions that require add-ons, but I don't think we need them for today. And I'll post about what those are, and you can just download them. If you have the student license thing, then you should be good anyway.
Okay. I think I downloaded most of them when I installed it, but we'll see.
Okay. Cool. So yeah, I guess we'll start with the time domain. And so it's this idea of quantization, right? So you start out, you're looking at digital signals, so they're quantized. And the quantization is time and magnitude. So if you start out with an analog signal, I don't know, can you see my mouse?
Yeah, I can.
Oh, sweet. All right. So yeah, you start out with an analog signal. If you go time discrete, that just means that, the computer has its internal CPU that's running, right? So it can only sample and record the value of a signal at specific moments in time. So that's your discrete time aspect. Then you have a quantized signal. That's the level of the incoming signal. Because if you have, let's say, a 3-bit number, so you're counting, 0 to 111, that's 7, right? So you have 8 values that you can record in, let's say, volume level. So it's also quantizing the actual amplitude or the magnitudes of the signal. And so if you put that together, you wind up with your digital signal. It's quantized both on both axes, essentially. So there's this analog digital relationship. Most importantly, I guess you need to just start with this from physics. The period of a signal is just 1 over the frequency. So you have your continuous time, those are analog, and that's your time values. So if you look at this signal, this is just a piece of a sine wave, right? It's continuous in time. And then if you sample it though, let's say you're only able to sample at certain time intervals, that's these red points or red lines here. And so you're sampling at specific moments in time. So it makes sense if you have this, you have these fixed time points that you're able to sample at. Instead of tracking what exact time value it's at, instead of doing that, you can just say, all right, let's just say that that we're sampling at a fixed rate, right? And then we can just keep track of which index each sample is. So you have the 0th sample, the first sample, the second sample, third sample, right?
Okay.
And so digital uses index values. And so in order to relate the real world time to the digital domain, you have this sample time and sample frequency, which is obviously just 1 over the sample time.
Yeah.
The sampling, it's actually sampling interval, but anyway, sampling period. But yeah, so basically you're just saying that, you know, this distance here is a certain time interval apart, right? So you might say you're sampling every, you know, 2 milliseconds or something like that. And so if you want to get what the actual time value is, that's where this equation kind of comes in handy. I'll post this slide thing, like all the slides, onto the Slack. But yeah, so if you want a specific moment in time, you can just multiply whatever sample you're at times the sampling interval, and that'll get you kind of like where you are in the real world time domain. And then you can also just do, you know, replace the t with the 1 over f. One note, in analog, this is just convention. Unfortunately, MATLAB doesn't always follow this, but I try to when I'm writing code and when I'm talking about this stuff, and a lot of textbooks do as well. When you're talking about analog values, they're lowercase. The exception is capital T, because that's for period. But analog values are going to be lowercase, and then digital values will be in uppercase.
Okay.
Just makes it a little easier. So yeah, and so what's interesting is this sampling frequency. You're talking about the sampling, but just note that it is still an analog value because it's samples per second. You're still relating it to a real world kind of thing. So then we get into frequency. So you have your analog frequency, right? And I mean, it goes really as high as you want, but what we hear is from like 20 to 20K. But the thing about analog frequency, so you have just, it's F, right? And then you have your sampling frequency, but analog frequency doesn't have a limit to it. You could go as high as you want technically, right? And so, you know, it's different with digital frequency because there is a range. If you're only sampling, you know, like modern systems, they usually, like for music, they'll sample at 44.1K. And, you know, if you're sampling at that, you can't record values that go beyond that, right?
Yeah.
You can't record anything like, oh, this has a frequency that's faster than what we were able to measure. So because of that, we use this capital F, digital frequency. And so it's just a percentage of your sampling frequency. So it's your incoming signals frequency divided by the sampling frequency, or like the max frequency.
It just normalizes it, right?
Yeah, so I mean, what you're doing is you're basically mapping this digital frequency in between 0 and 1. And a lot of people will also talk about negative 1/2 to 1/2. It's the same thing, and it's just because the way that frequency works, without getting really into the math, is it kind of like is cyclical. And so it'll repeat itself. So if you say 0 to 1 or negative 0.5 to 0.5, those ranges will be kind of the same thing.
I have a question. I really like the audio spectrum image and graphic that you have. Do you have a link to any of these images at all? I'd like to you know, maybe reference or use it sometime. That'd be really cool.
Unfortunately, I just shamelessly stole from the internet. I don't know. I mean, if you don't publish it as like a thing you're making money off of, I'm pretty sure you can use it. But you'd probably want to cite it, I guess, if it was going to be a more professional thing.
Yeah, no worries. I'll try to find it then.
Yeah, there might actually, from the file, you might be able to like reverse image search.
Yeah,
so
you could probably do that.
DSP.
There you go. So yeah, so what's interesting is there's this concept of aliasing, and so you actually can't record past half of your sampling frequency. rate without getting aliasing. And it basically is like a distortion to your signal. It basically means that you're not going to record the signal that you actually think you should be recording. So that's why modern systems, like if this is, I opened up Ableton and it's recording at 44,100 samples per second. We can hear up to 20K. So if you record a little bit past that in terms of your sampling rate, then the max frequency you can record is like 22K, right?
Yep.
So, and then this just kind of shows you the digital frequency. So it's symmetric. And usually because we can't record past 1/2 the sampling rate without aliasing, you usually just are interested in 0 to 0.5 or, you know, that kind of chunk. So all this is good so far?
All good.
All right, sweet.
One question. Is the frequency from 0 to 1 or from negative 0.5 to 0.5, that's entirely linear, correct? It's not logarithmic?
Well, so it depends how you're displaying the data. Like here, I have it in dB.
Okay.
dB is going to be logarithmic.
Logarithmic.
But you can display it not in dB, and it, depending on what you're doing, it's advantageous to have one or the other.
Okay.
But luckily, when you're writing stuff in MATLAB, I mean, it's just a matter of changing the code.
What you put in. Okay, sounds good.
All right, so going out of the whole time and frequency and back to the idea of a system, right? So we have this input, some system, and it gives you some output, right? There's this question of like, if you can get the essence of a system, like what it's doing, simply. And so there's these two principles of linearity and time independence, and it's so common throughout signal processing that they just call it LTI. Basically, linear means that it obeys what you'd expect with scale. If you input x equals 10 and you get y equals 5 on this graph, right? Then if you input 20, you'd expect to get 10. So you're like, oh, okay, it's just having whatever the input is. Then there's this idea of time independence, which is just if you start the signal at a particular moment in time, and you start applying that signal to the system, it's not going to be any different than if you applied it at any other point in time. So yeah, it actually, do you guys know what an LFO is?
Oh, I've heard of it, but not off the top of my head.
Okay, so let me try. Let's see what happens. I have Ableton opened here. And let's see. So what I did is I kind of made, first of all, can you hear this?
Yep.
Right, sweet. So there's this LFO down here. So there's this instrument. If I turn off the LFO, right, it just outputs a sound. And so you can see the pitch here in frequency. And so if you turn on the LFO, it's this low frequency oscillator is what it stands for. And so it's oscillating at this really slow rate, and you can change the rate. Right? So the interesting thing is if you can set it for two different modes. You can basically say that it's going to re-trigger the LFO, and so the LFO is going to start from the same point like every time you hit a note. So, right? Or you can set it to free running. So it's essentially just this continuous sine wave that's running in the background while we're talking. And so now if I start it at any given point in time, right? So it's just, so that when you have this thing and it's not re-triggering on every single note, that would be time dependent, right? Because it's actually looking at the moment in time. But then if you have time independent, these systems are a lot easier to classify and talk about And so that's usually what we're gonna work on. And it's what lets us kind of generalize the system, predict the behavior. We can make these. We can still make them because it's just a matter of coding them. However, the analysis on them becomes considerably more difficult. And actually, in truth, I haven't really done that much analysis on really any analysis almost on time dependent systems. But making them is a different thing than understanding them. So if there are functions that, you know, require that, like if we wanted to make an LFO or something like that, making it is a lot easier than actually explaining how it's working.
Okay.
All right. So then this whole concept of LTI is really useful because we said it's linear and time independent, right? So the idea is that we can predict any response to the system. So if we input, like one signal, right, like a little like boop into the system, we might get something like this that comes out, and so it, just kind of decays. So this would be like an echo kind of thing, right? But then if you input like two of those like boop kind of sounds, but like spaced in time, you would expect that you should just get this response repeated in time. And so if you kind of like have an input, then you have another input and another input, right? And so they all kind of build up on each other. So it's this idea of superposition, which you've probably done in like differential equations. But yeah, the inputs and the outputs kind of just stack. And that's because of that linearity and that time independence. So what is useful to know about is the unit sample sequence. So in continuous systems, you have the delta function, direct delta function. It's the impulse function. So have you heard of this or used it or anything like that?
A little bit, but not fully.
Okay, here's like a really hand-wavy explanation of it. Is you take a box that has an area of 1, right? And then we're going to shrink the width of that box by 10 and multiply the height by 10. And then just imagine you keep doing that. Eventually you get something that's really, really infinitely narrow and infinitely tall, but the area of it is still 1, right?
Mm-hmm.
And so that's kind of what's used in continuous systems. The idea being, let's say you're in like a big concert hall or something, right? That's going to have, if you like clap, there's going to be an echo that comes off of the walls, and it's the sound waves hitting, and you get the earlier reflections and then what's called late reflections as they come back at different rates, right? Mm-hmm. And so this like hand clap is your impulse function essentially. And so what you'll do if you want to like get the characteristics of a room is you'll go in with like the loudest sound you can get. It's usually like a gun or they have like a giant balloon and they'll pop it. It makes a loud, really short sound. And then you can record all of the responses, all the reflections. And so that's kind of what you see here. You have your direct sound, and then a short while later, you get different reflections from different parts of the room. And so if we're talking about it from a systems perspective, you have this impulse input, this delta function. It gets input into this system, which is this unknown black box kind of thing. And then we get out some impulse response. So your delta function just looks like that, kind of shocks the system, and then you have the response to that shock.
Okay.
So continuous time systems, that's the same thing. Oh yeah, okay. So then discrete time systems, these are a lot easier, I think. That's wrong, that's not H of n, it should be this. But I guess I didn't move it. But yeah, so it's this, we still use dn, but it's not really called a delta function, but I call it that sometimes. But it's the unit sample function, really simple to define. It's just 1 at the time, the n index value of 0, and then it's 0 everywhere else. So really, not that hard. But it's essentially what you would want to be inputting into a system in a digital domain, because you can't have an infinite magnitude.
I just wanted to add, even though you can model, you can simulate the unit sample response and impulse response, it's really, I don't think we have any piece of EE equipment that can send an impulse, right? Correct me if I'm wrong.
Yeah, I don't think so. I mean, you could use, like, I guess a pulse. You can do a pulse on the function generators.
Well, no, like not like that pulse, where the magnitude is infinite. So I remember, 328, the lab being just, the closest thing we'll get is we'll just send a rectangular function. Remember that the block that you had, the wider one, just so that we could take that derivative, and basically that will be the impulse response.
Yeah, there's interesting, like, I guess, like, hacks you can do to kind of get around that. I forgot about that derivative method, but yeah, that's like a pretty good way to do it. Yeah, that works. But yeah, in digital, I mean, luckily it's you just put a 1 in, and everything works out. I'm not exactly sure why that is okay, but it seems to be. So the math works. So yeah, so you have this unit impulse input kind of thing, and then you have your sample sequence, like, response that you get. So the response is the output to the sequence. It tells you this direct relationship between the input and the output. So if you just look here, you have, like, the impulse input, right? So same as before, but now it's a 1 and all zeros, these little blue points. And then you have your H of n, your output, and these are discrete samples in time, but it's still the output of the system. And so what you can do is you can treat the input, any input, x, as a linear combination. So it's shifted and scaled versions of this. So if you imagine you have this x of t right here as your input to the system, you could also model that as just a bunch of these little impulse functions, just move throughout time and scaled in magnitude. And because of the linearity and the time invariance, this will work.
Yeah.
So yeah, so it relates. So unit sample response, same thing. We're just shocking the system a lot of times, and then you have multiple responses. All right, so this kind of comes to the idea of a transfer function. I'll go back actually first. So I guess what's interesting here is if you put in your input being just like that 1, right? Then you would say that what the system is doing is pretty much everything else. Because before, I mean, we were just putting in a 1 and we got all this stuff out, right? So all of the information is contained in here, which means that we're actually multiplying, in quotes, the input by this H of n. And it's actually not quite multiplying, it's convolution, which you might have done in DE. But yeah, anyway, luckily we don't need to know convolution, at least not yet. So MATLAB will usually handle all of that stuff. But we can also describe this H of n by the transfer function. So it's commonly written with an H in here, but H is just equal to Y over X. So it's your output over your input. Whatever is in your output, whatever you get out, divided by the input. So when you input 1 and you get out 5, I mean, it's just like a scalar gain, right? Okay. And so that's kind of how you can think about these things. What we need for today is MATLAB represents these Y's in terms of BKs and the X's in terms of AKs. So yeah, and then you can, if you're given, we'll eventually go into like how what makes up these individual components, but not this week, I don't think.
Okay.
But if you're given a transfer function and you're told, oh, this system has these as the numerator coefficients and these as the denominator coefficients, that's really all you need in order to classify what it's going to do and to run it on any input that you can give it, like in MATLAB.